Chapter 2 is dealing with quadratic functions, and right off the bat in section 2.1 we're asked to deal with transformations. So when we look at these first 6 equations and the graphs that correspond beneath, we might notice a few things, such as 3 of these parabolas are facing upward and 3 are facing downward. Some of the vertices are above the x-axis, some of them are below, some of them are shifted to the left, and some of them are shifted to the right. Well, to use that vocabulary would suggest that we understand what the parent function looks like. What's shown on the left here is the parent function f of x equals x squared. And I'd like to compare it to the function we were graphing in the last chapter, the absolute value of x. Instead of just taking f of x equals x, we had the absolute value, now we're squaring, but there's similarities here. Remember some of the things that we could do to transform absolute values with putting a value out in front, the amplitude or the b, the h, and the k? Well, we can do all of the same things here, and they're going to have all of the same impacts. It turns out that all 6 of these functions written over on the right are in what's known as vertex form. If you notice these light colored, the 1 and the b over on the left, those values don't appear. They're not asking us to shrink or stretch or reflect horizontally in any of these. But we are shrinking or stretching vertically, and we are shifting. In vertex form, the vertex is h comma k if we are in the form that's written where it says vertex form. So when you see that the graph A, lowercase a negative should suggest that we're flipped upside down, and h value of 2 suggests a shift 2 units to the right, and then a k value that doesn't seem to appear would be a 0, so it would seem like if we looked at graph D, we would have our value. If we look at B, we have an h value of 2 and a k value of 2, so 2, 2 should be the vertex, but we're also oriented upward, so it would look like C. Pause this video for a second and see if you can match the others. Quadratic functions have a highest exponent of 2, and when we graph them, they look like parabolas. We're told that a can't equal 0 because if we multiplied 0 times anything, we would get 0, and so we would simply graph a constant function, not the U shape. Values of h and k shift things horizontally and vertically, and I think it's best to look at examples to understand that. So let's work on graphing x plus 4 squared minus 1. The first thing to consider is that it should read x minus h squared. So x minus a negative 4 helps us to understand that we should be shifting 4 units to the left. The minus 1 is consistent, so we should be going 1 unit down. When we look at that graph, we can see how G is a translation of F. If you consider the monitoring progress equations down below, remember that the vertex is h comma k. We do have x minus 3, so 3 comma 0 is our vertex for the first one. Minus 2 for number 2 should give us 2 comma negative 2. And then the plus 5, it could read as minus negative 5. It's at negative 5, positive 1. Now we can turn our attention to reflecting both horizontally and vertically, and we can also shrink and stretch horizontally and vertically. The negative out front is going to flip vertically because regardless of what we plug inside with x and square it, that'll come out positive, then times the negative will flip over the x-axis. Over on the top right there, when we put the negative on the inside with x, inside the parentheses, take whatever value you want for x, multiply times negative 1 and square it, it will always come out positive. It's more difficult to tell that this is a reflection in the y-axis because of the axis of symmetry. The pieces that are on the left translate over to the right and vice versa. It's difficult to see that, and that's why in just a moment I'm going to work on this graph that you see over on the right. We can also horizontally stretch or shrink something by placing a value other than 1 or negative 1 inside the parentheses. Let's say, for example, we take a 2 and so it's 2x and we square that. Now that's going to become 4x squared. that's going to act as a horizontal shrink. If we took a number like 1/3 and we squared that, that would become 1/9 x squared, and that's going to behave as a horizontal stretch. So values inside the parentheses that we multiplied times x have a reciprocal nature. If we see something is a value greater than 1, that's going to be a horizontal shrink. And if we see a value between 0 and 1, that's going to be a horizontal stretch. If you want to include a negative in that, then you can simultaneously stretch or shrink and reflex, but we can deal with those as separate entities. If we consider the amplitude being the a value on the outside, when we get a value greater than 1, it vertically stretches, and between 0 and 1, it vertically shrinks. So you can see those examples, and I think the arrows that they're pointing out there in the lower situations are beneficial to us. But I would like to take this function f of x equals x minus 3 squared plus 4 and change that a little bit. I think it'll help us see how things manipulate. So let's first take a look at a vertical reflection. So we should reflect over the x-axis. Our parent function is written down below as f of x, and to get the vertical reflection, we have to put a negative in front of the function. When we do that, it's probably better to distribute that negative, and so we would get negative parentheses x minus 3 squared, and we do distribute it over to the 4, so it becomes a minus 4. When we look at the graph, it should make sense that 3, 4 has shifted down to 3, negative 4, and what was oriented upward is now downward. The horizontal shift is going to get us across the y-axis. In order to do that, we put the negative on the inside of the parentheses. So you can see down below that we do that. And when we do, inside the parentheses, we have negative x minus 3. Well, it would be better if we could make that x positive. So we can factor out the negative, and notice it changes the minus 3 to a plus 3, yet the negative is still inside the parentheses. If we were to square that, that could come out as a positive 1, and so we wind up with x plus 3 squared plus 4. When we graph that, it's a reflection over the y-axis. An interesting question might be, what if we put the negative on the outside and the inside? Do those two undo each other? Do we wind up back at the same location? Well, remember, one's a horizontal reflection and the other is a vertical. So if we put the negative into both and we deal with the order of operations, let's deal inside the parentheses first. When we do that, we should wind up with the x plus 3, just like in the last example. And now when we deal with the outside, with the amplitude, and distribute that onto the 4 as well, we'll find out that we have reflected across both the x and the y-axis. So our vertex that was in the first quadrant is now in the third, and what was oriented upward is now downward. The lower left-hand corner talks about a horizontal shrink or stretch. I'm considering now that we're going to plug in a value of 6, which is actually going to be a horizontal shrink. You can see that the blue arrows in the lower left-hand corner are pointing toward the y-axis. That's what's going to happen here. When we plug in the 6, we get 6x minus 3. It's easier to graph this thing, it's easier to understand where the vertex is if the x has a 1 in front of it. So I want to factor out a 6, but notice that changes the 3 to a 1/2. If you're not sure, go backwards, distribute the 6 and get the 6x, and 6 times 1/2 gets us back to the 3. Now, to finish this up, to understand maybe even a little bit better, if we take the square and apply it to the 6, we could bring it to the outside as being a 36. So if you want to think that this is going to look like a vertical stretch, which means it's going to be narrower, I agree with you. But it doesn't impact where the 4 is, and it did impact where the 3 becomes a 1/2. When we graph this thing, look where it winds up. It shifts, or sorry, it shrinks from a vertex at 3, 4 over to 1/2, 4. So it's like an accordion. Yes, it's getting narrower, but it's getting narrower because everything is pulling closer and closer to the y-axis. A horizontal stretch is going to unfold when our value of b is between 0 and 1. So I'm putting in a 1/2 here. And when we work that in, it's easier to understand how this manipulates if in front of the x is a 1. So I'm going to factor out the 1/2. And just to be sure, if I go backwards, 1/2 times x is 1/2 x, and 1/2 times 6 is 3. If we deal with the 2, the square, 1/2 squared is 1/4, so it's the same as 1/4 x minus 6 squared plus 4. So it is again going to look like a vertical shrink, even though it's a horizontal stretch. If you're looking at the example over on the far left, those red arrows are pushing us away, but it's away from the axis of symmetry here. When we graph this thing, you can see that the original vertex at 3, 4 has stretched over to 6, 4. It's twice as far away from the y-axis. Why? Because our b value was 1/2. So it's the reciprocal, it's 2, it's twice as far over. And again, if we want to get from our original vertex 3, 4 to 4, 5, we go up 1/1. Now because we have stretched by a factor of 2, to get from 6, 4 over to 8, 5, we go up 1 and we go over 2. Vertical stretches and shrinks are listed in the bottom right-hand corner, and if our value of a is greater than 1, we have a vertical stretch. I want to do that. I want to put in a value of 2. So I'm going to take my original function and multiply it times 2. When I distribute the 2, I'm going to wind up eventually with 2x minus 3 squared plus 8. So notice that in vertex form, my vertex is now at 3, 8. That's not a vertical shift, it's a vertical stretch. And to highlight that a little bit more, I plugged in a couple of other points of note. It's one thing to get from 3, 4 to 3, 8, but also look, to just move one unit over to when x equals 4, in the original function, to get from 3, 4 to 4, 5, we would go up 1 and over 1. In our new function, to get from 3, 8 to 4, 10, we have to go up 2 and over 1. Why do we have to rise 2? Because we have vertically stretched the function by a factor of 2. Now if you notice, I'm going to multiply my parent function times 1/4. That should amount to a vertical shrink. And if I distribute that 1/4 onto the parentheses and the 4, it should be 1/4 x minus 3 squared plus 1. So take a look at where my vertex winds up. And also, again, if you notice how in the parent function we go from 3, 4 to 4, 5, up 1 and over 1, now if we go over 1 unit to 4, we're only going to rise 1/4 because we've vertically shrunk. You can say this looks wider, and it does, but it's as though the x-axis is behaving like a magnet, and it's drawing all of those points down closer to the x-axis. Although we don't want to neglect b, the real key things are a, h, and k when we're talking about vertex form. So if we take an example where we take the parent function x squared, and we're asked to vertically stretch by a factor of 2 and reflect in the x-axis, and also translate 3 units down, we want to check to see that a vertical stretch means that our amplitude should equal 2. Also, if we're going to reflect, the amplitude should be negative. And finally, if we're going 3 units down, that's our k value. So we want to take that original function and we want to multiply it times -2 first order of operations, because then it says followed by. So what comes afterward is to shift 3 units down. So that should look like -2 x squared minus 3. There's no parentheses because the h would just be a value of 0, and it can simplify to what we're looking at here. Example 4 asks us to translate to the right and up and reflect across the y-axis. That shouldn't be too difficult, but the challenge is the function is x squared minus 5x. That's written in standard form, not vertex form. We'll talk about standard form later. But the thought is, if we're going 3 units to the right and 2 units up, then we have our values of h and k, and across the y-axis we want to have a b being a negative value. So the first thing we want to do is take that original function and subtract 3 inside the parentheses and add 2 on the outside. So this is the tricky part. Wherever we see x, we want to subtract 3. So notice where the 3 appears twice, and then we add 2 at the end. That means that we're going to end up getting a trinomial minus a binomial plus this constant 2. And if you're not sure, just remind yourself of what it means to have x minus 3 squared, and also to distribute the negative 5. When we collect terms, we get x squared minus 11x plus 26. But notice I haven't dealt with the third component there. We want to reflect across the y-axis, so b needs to be negative. So again, wherever we see the x, we want to insert a negative value. If we square a negative x, we come out to a positive x squared. Then the minus a negative 11x is going to be plus, and plus 26. You weren't asked to graph this, but I thought it might be worth it to take a look. This is in standard form. The x-intercepts are at 0 and positive 5. When we're asked to shift 3 units to the right and 2 units up, it looks like this. You can take any point, translate 3 to the right and 2 up. If our original axis of symmetry was when x equals 2.5, you don't have to worry about that so much yet. Our new axis of symmetry is going to be at 5.5, 3 units to the right. And finally, when we put the negative in and reflect across the y-axis, then our new axis of symmetry is going to be at negative 5.5. You can see how we translate to the right and up, and how we reflect across the y-axis. Finally, a word problem. Flying fish use pectoral fins like airplane wings to glide through the air. Write an equation in vertex form, where the vertex is 33.5, to model the flight of the fish, assuming that it leaves the water at 0, 0. Okay, so vertex form, I know my vertex is 33,5, so I put those values in. The problem is, I don't know my a value. I'm not sure of my amplitude. But they do tell us that the fish leaves the water at 0, 0. 0 for x and 0 for y can be plugged in. And when we go to solve for a, we can get that it's a negative fraction. That should make sense because that's going to turn our parabola upside down. It's also going to be quite wide. So here is our function. And if it's graphed, it looks like this. You can see that the fish leaves the water at 0, 0. It hits a vertex at 33,5, and it should make sense if there's an axis of symmetry going through the vertex, then 33 feet later at 66,0, the fish should re-enter the water. Part B is asking us to talk about the domain and range in terms of the function. Well, what we're going to say for x values is that it's going to range from 0 to 66. The parabola could go infinitely, but that's not the context of the problem. You could think of someone trying to take a picture of this fish when it gets out of the water. It doesn't make sense to go underwater, so from 0 to 66. And likewise, the range or the y values, we're going to go from a low of 0 up to a height of 5. And in part C, does the value a change if the vertex is now at 34 as opposed to 33,5? Well, it should, because it's not going as far and it's not going as high, but let's do similar work as in part A to C. We plug in our vertex 30,4 for h and k, and if we're leaving at the origin again, we can plug those values 0 and 0 in for x and y, and we can work to solve for a, and we come to a negative 4 over 900. We plug in our equation, and when we graph these two, we can see, try to make some sense out of this. If the original function had a vertex of 33,5, then we should go from 0, 0 over to 66, 0. If our new function has a vertex at 30, 4, then we should go from 0, 0 to 60, 0.